All right. So today we go next step. We're slowly coming closer to the end of the lectures. And now we come to series elastic actuators. Right? So just to quickly remind you how we get here. Remember, we at some point in the middle of the course, we discussed DC motors and their properties, right? So it was perfectly reasonable. We understood how they work. Later, we discussed additionally the gearboxes, like how the transmission works, non-linearities that are characteristic for gearboxes. Right? Those things. And after that, a little bit about sensors, a little bit about non-linearities related to quantization, discretization. Now, we sort of saw quite a few problems now with those various types of transmissions, motors, etc. Now we will see one of the solutions that people provide for those problems. Right, and we will see how it ties together with our questions about transmissions, sensors, and quantization, discretization lag from the previous lecture. Okay, so series elastic actuators now. So before we can discuss them, we need to remind ourselves just a little bit what collisions are. Okay, because series elastic actuators are in many ways a reaction to the necessity of colliding with objects. Okay. So collision can be described, can be modeled in variety of ways, but we can distinguish two models: elastic and inelastic. Okay. So the simplest type of collision is one-dimensional collision, when you have objects that just move in line, right? Two-dimensional, you can imagine on a plane, it's like billiard balls, that would be two-dimensional collision. 3D collision is billiard balls, but in space, right? Okay, but one-dimensional collision is what you saw in high school, for example. Okay? So point-like mass, so we're not talking about the instantaneous change of, let's say, rotational motion. We're discussing only linear motion. And let's say this point-like mass is colliding with a much more massive body, like a wall, okay? All right. So elastic collision is characterized by conservation of energy. And in fact, the model goes kind of like this. The velocity after collision is equal to the velocity before the collision, but with the opposite sign. That is a characteristic of elastic collision. Okay. So this is the velocity before, this is velocity after the collision. So energy will be conserved in a perfectly elastic collision. In Russian, we call it абсолютно упругий удар. So the idea is that is a, how should I put it? I feel like maybe the English words elastic and inelastic are kind of slightly misleading here, because any collision in real life would be, in a sense, inelastic. They would drop some amount of energy, because pretty much anything that happens in real life dissipates energy, right? So like a football hit against the wall would be inelastic. Some energy will be lost, right? Whereas elastic collision is more or less a perfect model, is the ideal, which doesn't happen in real life. It is when all energy is conserved, right? So maybe absolutely elastic would have been a better word for it. But all right. Now, inelastic collision can be modeled very similarly. We say velocity after the collision is equal to the velocity before the collision with a minus sign, but additionally we multiply it by a coefficient. We call it the coefficient of restitution, right? Coefficient of restitution. This coefficient is usually between 0 and 1. Of course, you can try to come up with a coefficient of restitution higher than 1, which would mean that the velocity increased. And this is something that they used when they discuss explosions. Like if you have an explosion during the collision, the restitution can be higher than before the collision. That's because some of the chemical energy, for example, transferred into kinetic energy. But that is outside of the realm of pure mechanics, right? So we don't really have to think about it, right? And less than 1, you can think about it. Less than 0, sorry, you can think about it. Like, what does it mean? Right? Okay, right. Less than 0 would be kind of like penetration through the wall when you continue. Okay, all right. So perfectly elastic, velocity changed direction, but remains the same. Inelastic, velocity reduced by absolute value and changed directions. Okay. Now, we can consider kinetic energy in the inelastic collision. So kinetic energy before the impact was mv squared divided by 2, right? After the impact, same, but the velocity changed, remember? So after the impact, velocity is eta times v, right? V minus. This minus sign here is the indicator that it is before the collision, velocity before the collision. So what we have is eta squared times this value, which is just kinetic energy before the collision, right? And eta squared comes from opening the brackets on v plus, which is equal to eta v minus. All right. So we have kinetic energy after the collision being equal to kinetic energy before the collision times eta squared. The difference between those kinetic energies can be computed just as t plus minus t minus, right? T after the collision minus t before the collision, which is m v minus squared minus mv minus squared times eta squared. If we put it out of the brackets, we get this t minus, right? Kinetic energy before the collision, multiplied by 1 minus eta squared. And since eta less than 1, right, and bigger than 0, this coefficient would be positive and less than 1. Okay. All right. So we can expect the loss of kinetic energy to be equal to the kinetic energy or less, right? Something like this. Something like this. Now, this instantaneous change of kinetic energy implies that the energy went somewhere. It was transferred into a different type of energy. Usually in nature, energy does not just go away, right? Remember when we're talking about resistors, we were discussing the power of a resistor. What was the power of a resistor? Oh, power is a energy per time, right? How much energy per unit of time is being used, produced, added, subtracted, etc. That's power. So the resistor, the power of a resistor was, remember we said it was equal to the, how would you say it? Thermal power, heat power of a resistor. Basically the ability of a resistor to produce heat per unit of time, right? Heat energy. So a resistor was effectively a machine that transferred electrical energy that, for example, could be stored inside a capacitor or a battery, right? Electrical energy. it was transformed into heat energy, so something that could be dissipated, increasing ambient temperature. Right? Well, here, delta E would also have to be dissipated somehow, like it should be transferred into something. And what it usually is transferred into is either heat. If, for example, we are talking about a football, like balls that you play with, rubber, leather, etc., most of the energy would be transferred into heat, like it would collide, collapse, then stretch, etc. And this small motion would stop, and some heat would be produced. Fair enough, fair enough. If we are talking about collision of two metal balls, you would also have some heat produced between them. You can even maybe find some experiments on YouTube if you search for it. You would see that when they collide, they produce a little bit of heat, right? But for example, if you have a collision of a wooden object with a metal object, what you can expect is that some of the energy will be used to produce a lasting damage on the wooden object, right? You can imagine a dent. Imagine a metal ball colliding with a wooden wall. This wall would have an indent, right? A mark from the collision. This is a lasting damage that is going to be generated using energy, this delta E, right? And you can imagine quite a lot of possible versions of the same thing, right? Energy being transferred into damage. Right? Something can be broken. If you collide metal with plastic, it can develop a crack. If you collide with a glass, it can shatter. If you collide with, let's say, clay, it can change form without any restitution later. Okay. So lasting damage is a perfectly reasonable way to dispose of energy. Okay. All right, so let's keep it in mind that it is not only heat, but also lasting damage, permanent damage. Okay. So, now, robots tend to perform a lot of motions that involve collisions, right? So grasping something with zero velocity on during grasping, okay? Very typical. So you grasp something, but instead of doing it with like zero velocity very slowly, you do it rapidly, okay? Like this. Okay? There will be a collision. There would be a collision. Walking and especially running, your feet would come into contact with the ground at a non-zero velocity. Humans, when they walk, their feet come into contact with the ground with a non-zero velocity. There is a collision between the feet and the ground, even during walking and absolutely during running. Okay, there is a possibility to walk with zero velocity during the contact. It is just hard, and it is not energy efficient. So energy efficient gates usually include collision. Okay. Also, you can collide on accident, right? If you work around industrial robots, it is possible that you might come into contact with them. For industrial robots of the older types, such as what we currently use in production, this is undesirable. We specifically design them not to touch humans, as in we consider any contact between a human and a robot to be an unwanted scenario which we guard against. So we try to make sure that it doesn't happen. That is the current state of technology. Right? 1 second, I have a question. Okay, Ruslan, I will answer your question in just a second. It has to do with the format, so I'll finish my what I'm saying and then I'll go back. Thank you for the question. All right, so that is the current state of technology. Okay, we have this desire not to have those contacts between the robots and the people. But modern robotics have this whole separate branch of cooperation robots, right? We sometimes call them core robots. There are various ways. Basically, robots that are designed to be interactive. Robots, for example, for which you can teach them what they need to do. Like you can imagine a cooker robot that needs to grasp and pick and place. Okay, grasp, pick and place. Yeah. You can teach them by demonstration. Like take the robot, physically transfer its grip towards the object, make it pick, then transfer to the next place, make it place, and say, okay, this is good, repeat. It would be much faster than trying to program them. But for this to work, they have to be operational during the demonstration, because those robots, if they're switched off, you cannot move them. Remember during the lecture on gearboxes, we were talking about how some gearboxes are not backdrivable. Well, the types of gearboxes in KUKA are not backdrivable. You cannot physically move it with your arm. As in, when I say not backdrivable, I mean in a practical sense. I'm not claiming that it is absolutely impossible to backdrive them. What I'm saying is that a reasonable human will not attempt to do this, okay? So it is not a question of putting a little bit more pressure on them, It's like, it is for any practical sense, you cannot do this, okay? So you have to switch them on, and you have to run some control laws which would create compliance, so making them feel compliant, right? If they detect some pressure, they move towards where the pressure pushes them, and so on and so forth. This type of stuff you should, you either have been taught in Introduction to Robotics, or you will be taught at some later point. Okay, so there are those algorithms specifically for interaction with humans. But you can imagine this means collisions, because sooner or later, you will collide. Like, it's not always going to be zero velocity contact between you and a human. At some point, it will be non-zero velocity. That means a collision. Okay, so collisions have to be taken into account, right? Okay, now before we go on, so I hope this part hopefully I explained why collisions are important for robots. Now let me go back for Ruslan's question. So the question is, there was a mistake on the previous slide, T plus and T minus was changed in the formula. T plus should be with eta squared. Let me see. So T plus minus T minus. Yeah, the sign is one, right? The minus, yes. The eta should be here. 1 should be here. Yes. Thank you. It's very good. Yeah, and that makes sense because T plus is less than T minus. So this would be a negative value. What I should do here is just, as you suggest, put minus here, plus here, to be correct. Thank you. Very good. Good catch. Thank you, Russell. Okay. Now, what we said about collisions, what it comes down to is the fact that we will experience, how should I put it? We'll experience those instantaneous changes of kinetic energy, right? And those collisions will, as we say, pass through the motors. So I'm not proposing here to produce a theory of instantaneous changes of velocities for kinematic chains, right? So if you imagine a robot having like one link, right? Another link, maybe like one more link here, like, kinematic chain, okay? Like all of them move separately, nice and complicated. And we have a collision here, like a collision here. There will be instantaneous change in the velocity, right? It's like this joint will instantaneously change, this joint will instantaneously change, and so on. right? I'm not proposing to describe how it's done, but this theory exists. So we could write down those equations. We could do it, for example, by considering restitution on coefficient on kinetic energy. We could try to consider which quantities can be conserved, like momentum, and so on, like various rotational motions, like what is conserved, what is instantaneously changed, and then we would get a model for collision for multi-link robots. So it's not out of the question how to produce it. And you would of course, you can find it in the literature. But you can imagine what's going to happen is they are going to change, right? If your whole robot was just flying towards a wall, then there is a wall, it collides, all of the velocities would have to change. It's not like one of the links can magically continue motion, or it's not like one of the joints can continue rotating. Chances are all of them are going to instantaneously change their angular velocities and linear velocities. And chances are kinetic energy will be lost. As you can imagine, in real life, almost always collisions collisions mean that there will be some energy transferred into heat and possibly damage, mechanical damage, right? And this damage is going to be done not only to the structural elements that are directly in the collision, like by the gripper, for example. Imagine if your gripper is a huge metallic body. It is a big hunk of metal, okay? And your wall is also metal, all right? So you have a metallic gripper colliding with a metallic wall. Let's say that it is a high quality steel, very elastic. I'm not sure if you had lectures on different types of steel, but there are types which under collision do not deform. They act like a spring. So you collide, they receive no damage, they just contract, go back, and there's not a single scratch on the piece of steel. And it shouldn't be surprising if you ever saw like anything from like a hammer, for example, which collides very often with various objects, right? To like an excavator, they collide with all kinds of stuff, and so on and so forth. It's not surprising that there are types of steel which do not receive damage from collisions up to a certain point, okay? So you can imagine maybe your gripper is not going to receive any damage from this collision. But this damage can happen elsewhere. For example, inside your motor. If your structure is slightly more delicate in the motor, for example, if you have teeth of your gearbox, which are delicate and small, and suddenly you have instantaneous collision, which just jolts them into a different position, like they were moving around and then suddenly they have to stop. They're moving around and they suddenly stop. Maybe there will be a small damage. It doesn't have to be a big one. It can be just a small piece of metal being shaved off one of the tooth. And this, if it happens again and again and again, will accumulate and can lead to worse performance. It is not so surprising to see sometimes the bearings of gearboxes to be deformed, to be slightly misshapen, to stop behaving so well. Gears, especially regular gears with teeth, are often damaged. Right? There are other types of damage, like sometimes quite rare, I would say, but sometimes even the axes bearing the loads would be damaged. I mean, all kinds of things happen. Just as one example, sometimes even sensor can be damaged if, like this collision event moves, like there's a sensor plane, let's say, like it's placed very closely to the rotating shaft of the motor, right? And sometimes the shaft during the collision will just slightly shift its position. What can happen is the way a sensor is located, it will be just damaged. It will be kind of moved or cracked or whatever, destroyed. Those things can happen. Those later examples are, of course, bad design, right? It means that something was not designed well. But what I'm trying to say is the amount of things that can be damaged in the motor is large. Pretty much anything through which the collision passes is a candidate for damage. And we don't like this because collisions are not something that we want to avoid. Collisions for walking robots, for example, is a daily, hourly, like constant occurrence. You have to do it all the time, right? Each step is a collision. Okay, so imagine we just now to understand it mathematically. Imagine we replace our point-like mass with a pendulum attached to a motor, right? So everything would remain the same. It's just that instead of linear velocity, we have angular velocity. Instead of m mass, we have moment of inertia j. But we can still compute instantaneous change of kinetic energy, which would pass through the gearbox. Right? It can damage the gearbox. Okay, all right. Now we could imagine a different situation, right? Different situation would be if we had a spring between a point like body and a wall. Okay. So instead of having a point like body colliding with a wall directly, we'll have a spring between them. And as soon as the spring touches the wall and the body, right? Like it depends on where you place the spring. Let's say if it is attached to the point like body, then as soon as the spring also touches the wall, the dynamics becomes like this equation for this is the dynamics. Okay, so this is the dynamics. In this equation, K is stiffness and D is rest length of the spring. So as you can imagine, this model does not require a collision model. Like here we don't have to separately model how collision goes on. Why? Well, because instead, as we simulate this forward, we'll find that kinetic energy will be converted into potential energy of the spring, right? Kinetic energy is, remember, mv squared divided by 2. Potential energy of the spring is something like k x minus d squared divided by 2. Okay. With potential energy, it's always possible to add or subtract a constant, so we need to be careful, but yeah, something like this. And then after this, collision happens, the spring is being collapsed, right? It's going to then stretch out, right? And the body will fly away. So the potential energy would be converted back into kinetic energy, and if there was no damper, exactly as much energy as was put into the spring will be converted back, and it will be in the end the same as elastic collision. So velocity will be at the end of the motion exactly like it was in before, but the sign will be flipped. Okay. Now we can add a damper we can add a damper. We don't have to do it, without a damper. We can add a damper. And we can choose x such that z is equal to 0, just for simplicity, so the equations look nicer. It doesn't have to be this way, of course. So then what we get is mx double dot mu x dot kx equal to 0. So this mu is a damping coefficient, right? That's a damper. That's a force of a damper. This is the force of a spring. Okay. And this model is an inelastic collision. Essentially, as the body approaches the wall, it will be slowed down. Energy will be converted into potential energy of a spring. Then it will be converted back. And at the end, you would have a velocity opposite direction from what it was before, but less, because some of the kinetic energy would be converted into heat, and which can be computed by integrating the power of this force, right? So you can integrate the power of the damper, and this would be the amount of energy converted into heat. But you can imagine there is, again, no instantaneous change of kinetic energy. So there is no call for damage. You cannot say, oh, here is some energy which can be converted into heat or mechanical damage. You know that the entirety of energy lost here is converted into heat. Nothing is converted into damage. And this heat is being produced specifically in the damper. So not like in deformation of the rigid bodies or anything like that. All right. So you can see this is much nicer in terms of, if we are worried about destroying something, this is much nicer. This doesn't look like anything will be destroyed. Okay. You should, of course, like, reality checks are very important. So let's do just one reality check. If you have a very thick spring, so with a very stiff K, so your K is like 10 to the power of 5, okay, very stiff K. And if this kind of spring collides with, let's say, a wall made out of papier-mâché, or plaster of Paris, something like that, like a soft material, of course it will leave damage. No questions about it. Some materials just cannot withstand forces beyond a certain limit. So it's not like you can guarantee that there will be no damage in this case. But as you at least can guarantee that there is no jump of kinetic energy, which is a good indicator that maybe will be able to withstand, like survive, there will be no damage, right? But if you're interacting with destructible material or something like this, you have to additionally take into account properties of the material. Here we are thinking mostly about like a perfectly rigid wall, this perfectly rigid body, like a point mass, and we are basically saying that there is no instantaneous change of kinetic energy. If the scenario is more complicated than that, you have to take into account and write the model more complexly. Okay. All right. So this is a nice scenario. We don't have any instantaneous changes of kinetic energy. Okay. So the idea of series elastic actuators, CEA, okay, SEA, okay, sorry, series elastic actuators, SEA, is to add elastic element to the motor. Right? For example, we can add it after the gearbox and before the output shaft. So if you replace the point mass again with the pendulum, right? The pendulum kind of goes like this. Oh, let me use this. Okay, pendulum like this, right? And you can imagine it collides with something, right? Collision, not good. But you imagine that instead of a pendulum colliding with something, you have a small spring sticking out here. If the spring collides with something, much nicer. That sounds much nicer. Of course, this is not a very good model for what we are doing here. What we are doing here is essentially like a shaft, like a motor shaft that kind of rotates like this. Okay. And what we are saying is that at the end, there will be a torsional spring. Torsional spring means the spring that can wind up in like rotational direction, can rotate. And the more it rotates, the more torque it outputs. Okay. Deformation of the spring is rotational, not linear extension, but wind up, rotational wind up. Okay, so we add at the end of this shaft this torsional spring, and if the shaft collides with something, instead of the shaft instantaneously changing its kinetic energy, the spring starts to wind, you know, as like the shaft continues to move, but the spring starts to wind more and more and more. The shaft will eventually stop because the spring consumed all of its kinetic energy into its potential energy, and then it will unwind, and the collision thus happened not instantaneously, but over a period of time. So that is why you don't have a damage on this motor. That is an idea. Okay, let's look at a series elastic actuator and see if it makes sense. So there are many ways to do it, right? It is not just a single option. So consider a normal motor. Normal motor looks like this. We have a, let's say, a starter and a rotor. Starter, as you can maybe hear in the name, starter means static. So that means it does not rotate, right? In case of a DC motor, it will be outer casing and magnets, right? They do not rotate. More rotor is stuff that rotates. So, for example, in case of DC motor, it will include all the windings, all those wires. They're usually rotating. And of course, the output shaft. Then you would have here gears, cylindrical gears in this case, and the payload. Right? All of this rigidly connected, except here you have a gap, which, of course, this is where electrical fields act. Okay. Now, series elastic actuator allows us to put springs in various places. The most typical place is here. So we could put the spring between the payload and the output shaft. That is the most typical position, because payload is usually outside of our control. Some user will decide what payload is, and often it just changes. So integrating a spring there might be nice, but that is the question for the designer of the robot, not the question for the designer of the actuator. Instead, we could put it right before the payload. So if you imagine a motor with the shaft sticking out, right before the shaft, there would be elastic element, like a spring. Okay. By the way, it is a torsional spring, so it's not a spring that collapses like this. It's a spring that rotates. We will see it on a separate slide. Okay, so we can put it here, but also we could put it here, for example. So between the electrical motor and the gearbox is possible. That would not protect the gearbox from the collision, but it would protect the motor from the collision. So if the motor is your concern, then sure. You could also do exotic stuff, such as putting the spring, for example, here. So you would protect the whole motor, like allow the whole motor to kind of wobble, right? So in case of a collision, what happens, the whole motor, like gearbox, starter, rotor, everything kind of wobbles. Do you want this? Good question, right? Because then your starter would be not rigidly connected to the rest of your mechanical structure, and your mechanical structure kind of has this underactuated behavior, but it is possible, of course. And then you could try to integrate it somehow inside the gearbox, which I'm not going to comment on, but yeah, it's also possible. It's also possible. Some types of gearboxes naturally have some elasticity. For example, if we use, instead of gears, if we use belts. It is quite typical in buses. If you have ever seen how a bus looks like under the hood, you would see something like this, like a pulley, a bigger pulley, and between those pulleys there will be belts, right? Right, like this, belts. Those belts have some amount of elasticity, small enough, of course, but some amount. So you could argue that those belts automatically make the motor closer to series elastic actuator than to a rigid motor. If you're interested in this type of semantics, yeah. So there are options where to put the spring. Okay, if you're interested in more on this picture and more discussions, I will leave the link here. Like those, you can find this paper on the internet. For all other figures, I leave credit under the figure, so you can check it out. Now, how would it look in practice? Well, for example, here is the series elastic actuator. Here we have a DC motor. Okay, this is the stator of the DC motor. Here you have a motor, or rotor of the DC motor. Okay. Here, what we have is essentially, I would avoid like terminology, especially since some of it I don't even remember. But basically, here, what you have is connecting elements, like stuff that connects your output shaft of the motor with whatever comes next. Because the motors would be usually produced by a separate company from the series elastic actuator. Almost like it is quite rare to have a firm which would produce everything in-house. So it happens sometimes. But also quite typical to have one producer create electrical motors, one producer to create gearboxes, or in this case, series elastic actuators, and so on and so forth. So it's not always just like one company that produces everything. Okay, so this is just a connecting element. Now, it connects standard output shaft of your motor with your torsional spring. This is a torsional spring. So you can see it is basically some kind of wind-up structure, and it is designed like this, right? It's designed to wind up. You can rotate it, and it's going to create torque. Okay. This is your output shaft of your spring, if you want. Okay. Sorry. This part, this orange part, is just a finishing touch on this. Like those two elements together, they hold this spring. This is the output shaft. It's kind of weird, but in this case, this is the thing, right? It will be connected to this guy here. So like this will be connected here. Right. And the output shaft, you can say, of the motor, like it mechanically connected here and here and here. Okay. So your payload will be connected here, which would mean it would mechanically be rigidly connected to this guy. And this guy is the output of a spring, which is the spring is connects to this key. So there's a spring between the motor shaft and the output shaft, and this is the guy. This is the guy. Right. Good. So this is an option how you can construct a series elastic actuator. Of course, there are ways to do it, but this is one of the ways to do it. Series elastic actuator. Okay. Now let's consider for a little bit electromechanical model of a series elastic actuator. So let's say we have this as a model of our DC motor. So this is, remember, Kirchhoff's law. This is Euler's equation. So for a series elastic actuator, you still have the same Kirchhoff's law because the electrical part of the motor did not change. So it's actually, you would expect it to be the same, right? And it's exactly what you have, except I changed variables. So here we have omega, here we have Fm dot, phi m dot. I do it because for a series elastic actuator, you cannot use the trick of treating omega as independent variable. You have to consider rotations because of this torsional spring inside. Orientation of the shaft becomes important. So somehow you cannot get away with thinking that it will all come down to second order model. No, it will be like, it will be fifth order model, unfortunately.
Excuse me, we can't hear you.
Can you hear me now?
Yes.
Okay, sorry about that. Okay, let me go back a little bit, and I think maybe from here, this is where apologies. My mic, if you touch it, it will for some reason switch off, but not instantly, like after a second. So this time I didn't catch it. I thought it would, but I didn't catch it. I apologize. All right, let's repeat this. So the difference is we have this torsional spring, right? The torsional spring would act both on the internal motor and on the output shaft, right? So there will be torque from the spring that acts on the internal motor. It acts with a minus sign, and on the output shaft with a plus sign. Of course, the sign depends on the choice of these two variables, like their position. If you switch their position around, the minus sign will go to the other equation. Right? Okay, and you have a separate Euler dynamics here. So your output shaft acts as a separate body now. It would have its own inertia. And when you think about it, you're kind of tempted to say, well, this inertia is probably so insignificant, it probably doesn't matter. That is incorrect. That is incorrect. The reason it is incorrect is because you would have your payload sitting there. And when you put your payload there, the inertia of the output shaft would be much greater than the inertia of the input, like motor shaft, right? Not much greater, but greater, okay? Because payload would be significant. This oily dynamics, you can, like orange, you cannot get rid of it. Same, it is tempting to say, well, of course, output shaft makes sense because of the payload, so we have to take into account. But this green stuff, who cares about it? It's a small inertia. It's just a tiny rod of the motor rotating inside, maybe with some wiring, very small. Let's ignore it. You cannot do this either. And the reason you cannot do this either is because this tiny motor with a, some wiring rotating around, rotates on the opposite side of the gearbox. And if you remember, when you compute kinetic energy, if you compute it in terms of rotations of the output shaft, what will happen is this gearbox sort of multiplies the angular velocity when you compute kinetic energy. You can avoid this remembering any of this, just compute kinetic energy directly, right? Just compute it the way it is. But then, and then you would notice that this guy would be significant. It is just one of those things where it is easy to make a mistake. For example, if you compute phi in terms of rotations of the shaft of the motor, so the fast rotating shaft, the coefficient in front of phi would be small, same as this guy would be small. Why would they be small? Oh, because rotations are so fast. If they were big, that nothing would even rotate there. It's very fast motion. So coefficients there would be small. But if you change variables and you compute all of this, but in terms of rotation of the output of your gearbox, so you make sure that all of your angles are in terms of the output angle of the gearbox. So the same angle that comes into the torsional spring, then those will be significant numbers, right? Those will be significant numbers. So you cannot ignore either of them. Also, importantly, of course, here, this formula is designed for angles to be in the same radians. So you cannot mix, for example, make phi sub m to be computed in terms of radians of, let me go back so that you would see it more clearly. You cannot compute phi sub m goes here, right? This is phi sub m, and this is phi sub o, right? So it is their difference that is k times, let me write it here, phi sub m minus phi sub o. Okay. You cannot compute them in terms of radians of rotation of this guy versus radians of rotation of this guy. If there is a gearbox, let's say somewhere here, okay? If here we have a gearbox, we couldn't measure radians here versus radians here, because they are not going to be, that's not what this torsional spring experiences. What you would have to do is measure radians here, like after the gearbox, okay, versus radians here. So in this formula, unless you want to put gear ratio in front of phi m, which you probably don't want to do because there will be a whole lot of additional issues you could have. I mean, you could, of course, you just need to be careful. You probably would be better off just computing everything in terms of this same radians, right? So radians left of the spring, right of the spring. Okay, all right. Okay, so you can see that this model that we had previously is a second order model. We have two independent first order ODEs. First one, second one. Here, on the other hand, we have one ODE, first order, one ODE, second order, one ODE, second order. And because the zero order derivatives of both of those variables, phi sub m and phi sub o, enter into the equations, we can't really replace them with a lower order ODEs the way we could do here, right? In fact, of course, this is the spring model. What we would want is probably a spring damper model. So not only would have this k, phi m, phi o, we would also have some kind of mu times phi dot m minus phi dot o, and so on. So just a full-fledged second order systems, both of them, the motor and the output shaft. And this is a problem for model-based control, because suddenly from second order system, which is very easy to work with, we could understand it completely. We analyzed it. It has this critical damping, overdamped, underdamped. It has stability dependent on ratios of stiffness and damping. Everything is very easy to analyze. We could analyze its performance under different frequencies. It can be a low pass filter, high pass filter, can be bandwidth filter. Like all of it is so easy, right? Instead of that, we have a fifth degree system, which would have 5 different eigenvalues. Its behavior under in Bode diagram, you can expect, like we didn't study this, but basically you can kind of expect like 5 different changes in how Bode works, right? So it's going to be complicated. All of this is complicated, and this is a problem. This is why series elastic actuators is not as nice as DC motor, right? But on the plus side, it doesn't receive damage when you use it, which is a maybe more important aspect than the ease of use, right? And of course, same as with many other complicated things, we can try to make it less complicated by this like divide and conquer approach. For example, maybe you remember previously we were talking about how when we were discussing frequencies, like control frequencies, we were talking about how we could make a local control loop which would run on a higher frequency. That could be beneficial. Well, we can do the same here. For example, this can be made into a separate control loop where we would get desired I, right? This is what is typically done here when we want the motor to be acting as a producer of torque, right? Because the torque would be produced here, right? Here we can go even further. Instead of doing this, we can make it into a machine that produces desired values of phi m, okay? So, or even better, if you want, desired value of phi m minus phi o. But phi o is not under our control, so let's say phi m, phi sub m. So we could make a local control loop, which would specifically produce desired value of phi m. This would kind of imply that the system is maybe third order, because the second equation is still second order equation, or maybe we could get away somehow if we are careful with making it second order system. You have to think about it. But the idea is that you could make a local control loop which would kind of think that maybe this guy is external disturbance or just external input. We're not going to worry about it. Instead, we were just going to worry about producing k times phi m minus phi o to be what we want it to be. And since phi o is, let's say, slow, doesn't change as fast, we can treat it as constant or a slowly changing signal, which we can work with. And then we could do a control over something that is smaller degree, right? Like third order system, maybe second order system. That could be nice. That could be nice. This idea, let me now change the slide. This idea is treating series elastic actuator as a torque generator. Right? So this is what we call output torque. Tau sub O equal to K minus Fm F times Fm minus Fo, phi m minus phi O. So instead of trying to solve a problem of generating desired stable behavior of the whole system, we solve a problem of generating this output torque, which is done by controlling phi sub m. And then when we design overall robot, we assume that we have this ability to generate this tau sub O, which is then used for controlling the rest of the structure. Right? That is one of the typical motivations for using series elastic actuator. Instead of working with position control, or which is the way we say it. Now I'm starting to use jargon instead of science, so my apologies. But position control is what we call wooden. It's when you have a position control robot, it's kind of like a table, right? You can drop it on the floor or just bounce around and then stabilize. It's not going to be elastic. It's not like a human or an animal, right? It's not compliant. Instead of having option to do that, or alternatively having an option to do torque control, which is, well, let's say, more complicated in some way. Instead, what you can do is do position control on the internal motor, phi sub m, and the result is a torque control. So you can generate torque by doing position control on the internal motor. This is very nice. This is what we like. This is a popular motivation for using series elastic actuators. What you get as a result is a torque control, but what you do is a position control. Okay. To achieve this, often you have to measure both phi sub m and phi sub O. Now, let me just go a little bit back. Notice here, I think, well, we don't have the picture, but let me just illustrate how it could be done. We could put a sensor at the back here to measure orientation of this axis. And we put a sensor here to measure the rotation of this axis. And this would allow us to measure both phi sub O and phi sub m. And we need both of them if we want to control tau sub O. Okay. All right. Now, before we go anywhere, let us just solidify a little bit what this thing actually is. So this spring here that I draw on the slide, this guy, I didn't draw it. It was these guys who drew it. So this spring, it has an actual shape, which can be wild. So I'll just take a minute to look at those springs. So if you want sources for those springs, like where did they come from? Here are the references, but bibliography is in the source here. So you can imagine like this looks stiff because of the metal is so big, right? This, on the other hand, looks very compliant. This looks even more compliant. This looks super compliant. This again looks stiff, but also since it is very flat, it's probably not, inertia is probably small, which is nice. Here inertia looks extremely high. This looks like it would have inertia, but because of those small holes, the stiffness will be less, and also inertia maybe would be a little bit less. So it's a variety of designs is impressive, impressive variety of designs. Here you notice that they managed to reduce the amount of metal in the outer ring too. It's good, right? So those springs are not what my message is. Those springs do not look like this. That is not how the spring looks. Okay. A variety of designs can be used. Okay. Now, now we come to like one of those important intellectual parts of the discussion. It is a popular idea that we could
Excuse me, we can't hear you again.
Okay. Can you hear me now, right?
Yes.
Okay. Sorry. Can you tell me when I stopped? Like a second ago or longer?
I think a little bit longer, like a minute.
Minute? Okay, unfortunate. Right. So, can you remind me what was the last thing I said, so I don't guess?
I think it was on the previous slide.
On the previous slide?
Yes.
So you mean like
Ye-
this whole slide we didn't catch?
Yes.
Excellent. Okay. Well, let me go over it one more time. This next time, just do it faster. So I don't go over the whole slide without without you hearing. Okay. Thank you. Thank you for telling me. Okay. So there is this how should I put it? There is this problem or idea, I guess, that you could implement spring-like behavior for a motor using just control, right? You remember when we studied the motor? It was like we discussed that as a second order system motor. We discussed PID control for motor. Even when we discussed the motor model itself, all of this looked a lot like a second order system. So a spring mass damper. Any second order system is a spring mass damper in terms of a model, right? And we can intimate that if we can control it, we can make it behave the way we want. We can make it behave like any spring mass damper, like high compliance, low compliance, anything. So it kind of feels like, why not make motor behave like a spring mass damper and not use series elastic actuators? We could just do it programmatically, right? Why make mechanical changes? And in fact, when you go to, let's say, any class on core robotics, collaborative robotics, what you would hear is people would say, this is a mechanical compliance, meaning that there are springs somewhere hidden in the robot. So it is like series elastic actuator. And here is a programmatic compliance or control compliance, meaning that there is, what do you call it? Meaning that there is no springs, it's just programmatic behavior that makes something act as if there are compliant elements inside. Okay. Well, there are two independent good reasons why you cannot do this, why you cannot avoid collisions by programmatic behavior. Pragmatic behavior is good, it's just that it's not for collision, for dealing with collisions. Okay, so first, a collision event, as I said, is instantaneous change of kinetic energy, right? So it doesn't depend on control law. Like it doesn't matter what your robot, how your robot behaves during collision, like in terms of voltages and so on, because when collision happens, there will be change of velocities, some of the energy will be lost, transfer to heat, transfer to damage. That is it. It's you like what your voltage does in a sense is irrelevant, especially if you believe in it being instantaneous, right? Your voltage is just going to be there, just going to provide a constant torque acting on the motor shaft. So that is one thing, right? And in fact, this is true for a series elastic actuator too. It is just that some parts of series elastic actuator experience this collision. So output shaft experiences a collision, it is going to receive damage if it is designed badly enough to be damaged by collisions. But internal parts of the series elastic actuator are not going to receive damage because there is no collision for them. For them, what happens is slowly the torsional spring winds up, right? It slowly winds up. And potential energy increases, then decreases. There are other processes, but there is nothing instantaneous going on inside. So there would be no collisions inside. So that is the solution. For the output shaft, there would be instantaneous changes of kinetic energy. But we can design the output shaft to be very rigid. For example, it's not going to have gearbox, no teeth, like no like moving parts. It's going to be very simple. And this would allow us to avoid distraction because it's going to be rigid, like it's going to be robust. So it's not like we avoid collisions entirely. We just avoid collisions in the places which are vulnerable, such as gearboxes, DC motor itself, like the all those like small bearings and so on. All right, so this is the first reason. We can give a second reason. Second reason is control laws are usually discrete, right? That means that there exists a time scale on which control law does not change. Right? So let's say like 10 milliseconds, for example. What that would mean that there exists like those 10 milliseconds during which if the collision happens in those 10 milliseconds, control law doesn't react, it just stays the same. This is not a behavior of a spring mass damper. This is just a constant input for the differential equation. So your eigenvalues are not going to behave on these time scales, are not going to behave like you would expect them to behave. So it's just not a spring, right? Because, and this is just a problem of different time scales. If your discrete system does not operate on the same time scale as your collision, then instead of a spring mass damper, you have a rigid body colliding with a wall, right? Second, you always have a lag, time lag. So it means that when the collision happens, no matter your time scales, even if your discretization is very fine, you are reacting to something in the past. You're not reacting to what is going on now. Let's say your time lag is like 2 milliseconds. It would still mean that you are reacting right now to what happened 2 milliseconds ago. And during the next 2 milliseconds, you're not going to know anything about the collision. So your controller cannot, during those 2 milliseconds, cannot really do anything. And if damage is already done during those 2 milliseconds, too late. It's too late. Of course, to answer this, all of this, like everything that I said, you can reply that actually instantaneous changes of kinetic energy do not exist, right? It is just a model that I proposed. In fact, what happens during the collision, various parts of the robot start to bend elastically, right? There is a bending here, change of deformation here, slow change of kinetic energy here, and so on, right? Everything bends, everything slowly changes its velocity. Kinetic energy rapidly becomes potential energy stored in those deformations, then it is rapidly released back. And in fact, if the speed of those deformation processes is, roughly speaking, similar to your discretization step, so your control frequency, or if it is roughly on the same scale as your time lag, then maybe you could, in fact, use programmatic control to deal with all of this stuff, right? And then maybe you could even do this whole thing without worrying about series elastic actuator. Maybe you don't have to insulate your gearbox and everything else if your collision event is slow enough, right? But practice tells us that the solution is somewhere in between. You don't have to always use series elastic actuators, They're useful. You just don't have to use them all the time. There are alternatives, such as, for example, a lot of people like to use hydraulic parts in their machines or pneumatic parts in their machines. Pneumatic parts always act pretty much like springs, so they store potential energy very effectively. Hydraulic parts, they just don't break very easily. They're very robust. They don't store energy per se, the same way as pneumatic tubes do, like pneumatic motors and so on. But they are robust. You can make them robust. You can make them, you can insulate your dainty small parts from the collisions, because the collisions can happen mostly through the those large metallic parts which are directly connected to hydraulic parts and so on. Yeah, so there are ways to deal with this, right? Also, sometimes you install springs not at the motor, but at the end, let's say at the end effector. For example, robots typically have soft feet. The feet of the robot are at least a little bit soft. Like they're not metal. The robots are not metal walking on metal. They're usually slightly soft, and usually robots walk over slightly soft environment. When you pick and place something, you want to avoid collisions as well. So you make sure that either the gripper is soft or you grip soft objects, right? For example, if you grip boxes, boxes are soft, so no problems there. And so on and so forth. So the truth is somewhere in between. You don't have to use series elastic actuator for everything. The collisions are not instantaneous completely. But as long as this idea of instantaneous collision is close enough to what you actually experience, you have to consider all that I just said. So programmatic approach to this problem is valid and people use it. But people prefer to use it for lower timescales. For example, when you interact with a human, collision with a human would be a completely different time scale from a collision with a ground, for example. Because if the collision is initiated by a human, the human is not going to run into a robot at a high speed. It's going to be a very slow speed collision. And the human is not going to kind of like hit the robot with the knuckles, right? You're not going to use like this part of your body to attack the robot. You're probably going to use your fingers. And when your fingers go into contact, they're going to spend some time before they actually, push really and so on. So the time scale is different. On this time scale, your PID control and your other control loops would have enough time to react. Your discretization time step is not going to be a huge problem. Your time lag is not going to be a huge problem. So on those time scales, using series elastic actuator is unnecessary because you can do everything programmatically. So you have a variety of tasks. For some tasks, it makes perfect sense to use series elastic actuator because it just better suited. It actually protects you from real sharp collisions. Sometimes you don't have real sharp collisions, so you don't have this need. You need to be careful, right? You need to be careful to differentiate between them and to make your choices. All right. Oops, sorry about that. Okay. So with that said, this is it for today's lecture. And if for more material on those series elastic actuators, I would recommend you to maybe first go through the sources that I provided, but also just generally you can look up academic papers on them. The topic is interesting and very much alive. Currently in variety of robotic tasks, people are at the same time solving roughly similar problems with and without series elastic actuators. So kind of like looking into this topic is interesting for you as a professional, regardless of if you see yourself as an engineer or researcher. It's like one of those use cases where you can understand what the problem is all about, but the answer like what is the best way to do something isn't obvious. So it's just like interesting thing to spend some time on. Right. Thank you guys for finding time for today's lecture. If you have questions, please ask.